Hello everybody, my name is Joko Sampurno. I'm from UC Leuven, Belgium. Today I would like to share my work about assessing the impact of sea level rise on future carbon flooding hazard in the Kapuas River Delta. As we know, one of the impact of global warming is mean sea level rise, and this phenomena increasing the carbon flooding hazard in low-lying delta over the world. Carbon flooding is inundation that driven by a combination of two or more extreme events, such as storms from the ocean or intense rainfall over the area, plus high discharge from the upstream. As more and more people live in near the sea, future carbon flooding risk must be properly assessed for urban planning and coastal protection development. The problem is some local water management agencies in developing countries often lack data and tools to conduct such an assessment. Therefore, a simple but accurate tools is critical for them to assess potential flood hazards, mitigate the risks, and plan adequate measures. To tackle the issue, we propose a combination of machine learning technique based on the selected observational data and a simple beta inundation model to assess the future carbon flooding risk in the data scarce delta. As a case study, we implement this approach to assess future carbon flooding risk due to mean sea level rise in Pontianak, a city located in the Kapuas River Delta on the west coast of Kalimantan Island, Indonesia. Here we use river water level as flooding indicators. Based on observational data, the local water management agencies define 2.5 meters as threshold when water starts to overflow within the city. Then we choose a multiple linear regression algorithm, one of the simple machine learning algorithm, and we set 7 predictors: one from the ocean, which is the surface elevation; two from the upstream, which is discharge from two major rivers which flow to the city, and for weather situation over the area. Then, when the data set is ready, we split data set 80% for training and 20% for the testing. Then we train our model using training dataset and evaluate the performance in testing dataset. As you can see in the figure, we have good model with good consistency both in training and in the testing phases. After having the model, then we continue to predict the future by using mean sea level rise data from IPCC. Using this mean sea level rise data, then we modified our sea surface elevation data set as one of the predictor of in our model. Then we run again the model from 2020 to 2100. After obtain the output of the model, which is mean river water level dynamic, then we extract the flood frequency using return period from 1 to 100 year return period. Then we continue using the 100 year flood frequency period. We then applied simple beta inundation model to delineate the flood extent within the city, and then we assess this flood extent to buildings and roads within the city. As you can see in the table, if we use the current situation with 100-year flood scenario, 80% of building will be impacted and 70% of road will be impacted. But in the future, in 2100, if we implement low emission scenario, we have the impacted building will increase to 84% and impacted road will increase to about 78%. If we implement medium emission scenario, the impacted building will increase to 86% and impacted roads will be increased to 79%. The last one, if we implement high emission scenario, then impacted building will increase to 89% and impacted road will increase to 83%. So Here we can show you that integration of machine learning and simple beta inversion models successfully work on simulating water level dynamic and quantifying the flood frequency curve for current and future states as modulated by sea level rise. We found that the 100-year flood height for Pontianak will increase from 2.8 meters in the current state to 3.03 for low emission scenario, 3.13 for medium emission scenario, and to 3.38 meter for high emission scenario in 2100. This means that in 2100 more building will be exposed, increase about 4% to 9%, and more roads will be impacted, increase approximately 7% to 12%, depending on the sea level rise scenario we implement. Of course, this approach will benefit the local water managers in data scarce area to prepare adequate mitigation planning for managing the future component flooding hazards in their area. This is the end of my presentation. Thank you for your attention, and any question or suggestion are very welcome.